When IT teams attempt to scale virtual desktop infrastructure by simply piling more resources into a single massive cluster, the system doesn't get stronger. It creates a massive funnel where thousands of digital requests aggressively bottleneck until the central core collapses under the weight. Unlike web servers or basic storage arrays, adding capacity to a virtual desktop environment is not a simple linear equation of adding hardware to a pool. Pushing thousands of concurrent Windows 11 virtual desktops onto a shared monolithic infrastructure forces intense and unpredictable compute demands to compete for the same physical pathways, inevitably triggering localized bottlenecks. A handful of heavy power users can quickly turn into noisy neighbors, consuming disproportionate I/O and processor availability. This starves the surrounding virtual machines, dragging down the performance of the entire cluster. Past a certain threshold, attempting to fix this by blindly bolting on more servers no longer increases usable capacity. It simply enlarges the blast radius of a potential failure. To solve this, Nutanix engineered a specific validated design for Omnissa Horizon on AHV. This architecture was built to support exactly 5,000 concurrent Windows 11 users, deployed across an active-active multi-site configuration. The design carries a strict performance mandate. Every workload must operate with less than 5% CPU ready time to guarantee a zero-latency experience for the end user. Reaching this scale requires abandoning monolithic, infinitely expanding clusters entirely in favor of a strict, compartmentalized block and pod framework. By defining the strict physical limits of each hardware block and completely decoupling the virtual desktop control plane from the workload compute resources, the architecture isolates variables and mathematically secures system uptime. We begin at the smallest physical unit of this architecture, a single Nutanix AHV server rack node. Each node is tasked with supporting a specific knowledge worker profile running Windows 11. That means allocating 4 virtual CPUs and 6 GB of memory per virtual machine. Based on those compute requirements, we hit a strict physical limit. A single node supports exactly 100 Windows 11 desktops before hitting 85% CPU utilization. Exceeding this limit creates CPU ready time, where machines wait for an available processor, forcing latency to spike exponentially above our 5% threshold. That 100 desktop cap per node is an unbreakable law of physics for this design. Exceeding it translates localized hardware delays directly into a sluggish, unresponsive desktop experience for the user. Taking that single node's capacity, we group 16 AHV nodes together to form a workload cluster building block. To ensure continuous operation, this cluster operates on an N+1 resilience model. 15 nodes handle active workloads, while 1 complete node is held in reserve to absorb physical failures. With 15 nodes running 100 desktops each, the maximum safe capacity of a workload cluster is 1,500 active virtual machines. The cluster size is capped at 16 nodes for a strict operational reason. It ensures that the required maintenance windows for patching and updating the entire cluster remain firmly under 24 hours. By halting expansion at 16 nodes, we prioritize isolated failure domains and predictable maintenance cycles over allowing the system to sprawl into an unmanageable footprint. Providing these desktops to users requires the Horizon control plane, the connection servers, unified access gateways, and SQL databases that authenticate and route every session. To save on physical hardware costs, IT architects often run these management components on the exact same cluster as the thousands of desktop workloads. If a sudden I/O storm or a massive spike in processor demand occurs within the desktop pools, the hypervisor can choke. This starves the critical Horizon brokering processes of the compute resources they need to function. This diagram illustrates how the Nutanix Validated Design enforces physical separation. A dedicated 4-node management cluster runs independently from end-user desktop activity. Sized exclusively for infrastructure components, this management tier ensures high availability completely distinct from the workload block math. Isolating the control plane guarantees that heavy end-user compute demands will never crash the core systems responsible for brokering and managing the overall environment. Reaching the target requirement of 5,000 concurrent users dictates that we deploy 4 complete workload clusters to provide the necessary active capacity and failover headroom. These 4 workload clusters, along with the single isolated management cluster, are grouped into a unified logical structure known as a Horizon pod. Running a single pod inside a single physical data center creates a critical single point of failure for the entire workforce. To resolve this, we replicate the exact same pod architecture into a second, geographically distinct availability zone. These 2 separate data centers are connected using Omnissa's Cloud Pod architecture, operating over a network link with less than 5 milliseconds of latency. Global entitlements layer on top of this connection to create a single logical namespace. Under normal conditions, this system actively and evenly distributes the 5,000 users across both physical sites. Local high availability keeps a single site running during hardware maintenance, but true enterprise resilience requires this federated, active-active multi-site architecture. Consider a scenario where a massive power grid failure causes Data Center 1 to go completely offline. The data traffic routing instantly detects the drop and redirects to the surviving site. Inside Data Center 2, the isolated management cluster immediately absorbs the massive influx of user authentication requests without competing for resources against active desktop sessions. Because of strict N+1 capacity planning, the 4 workload clusters in the surviving data center possess the mathematical headroom to automatically spin up the displaced desktop sessions without requiring manual IP rerouting. This design systematically eliminates the unpredictable bottlenecks and localized failures that plague monolithic virtual desktop deployments. Expanding the environment further is no longer a custom engineering exercise. It becomes a simple process of adding another predefined 16-node block to the exact same specifications. By capping node density at physical limits, isolating the control plane, and federating identical pods, delivering 5 nines of virtual desktop uptime becomes a repeatable mathematical certainty.